Hey there, and welcome. Have you ever really thought about how a campfire turns a log into ash? Or how baking soda makes your cookies puff up in the oven? Well, it's not magic, it's chemistry. And really, chemistry is just the story of how everything around us changes. So today, we're going to learn the language of chemistry and how to read those stories.
So, let's just jump right in with a question, right? Think about a rusty nail versus a melted ice cube. I mean, they've both changed, obviously, but the nail has become this totally new, kind of crumbly reddish-brown thing. Meanwhile, the ice cube is, well, it's still just water, just in a different form. So what's the deal? Why the huge difference? And trust me, by the end of this, you're going to know exactly why.
All right, to get to the bottom of that, we first got to understand that there are two fundamental types of change that can happen to anything in the universe. Let's break them down.
So on the one hand, you've got a physical change. Think about melting chocolate. It goes from a solid bar to a liquid puddle. But you know what? It's still chocolate. You could cool it down and get your chocolate bar back. But on the other hand, you have chemical change. This is like baking a cake. You mix up flour, eggs, sugar, and when you're done, you've created something totally new. And the big takeaway here is you can't unbake that cake. A brand new substance has been created.
Okay, so if you're going to track these massive, permanent changes, scientists realized they needed, well, a language, a super precise, universal way to write down the recipe for how one thing turns into something completely different.
And that, my friends, is the chemical equation. You can think of it as the ultimate recipe for a reaction. It uses special symbols to list all the starting ingredients and then tells you exactly what you end up with. It's an entire story told in a secret code of symbols.
And every single one of these stories has two main types of characters. The before characters are called the reactants. Those are your starting ingredients. And the after characters, those are the products, the totally new things that get formed. You start with reactants, you end with products. Simple as that, right?
Now here's a super famous recipe, making water from hydrogen and oxygen. But wait a second, look closely at the atoms here. On the left side with the reactants, we're starting with 2 oxygen atoms. But then you look over on the right at the product, and there's only 1. Huh? Where did the other atom go? This just can't be right. This recipe, as it's written, seems to be breaking a huge law of the universe.
And that law is the law of conservation of mass. And this is the big one. It basically means you can't just create or destroy atoms during a chemical reaction. They just get shuffled around. They find new partners and get rearranged into new molecules. Nothing ever just vanishes into thin air.
So, how do we fix our water recipe? We balance it. See what's happening here? We add these big numbers out front. They're called coefficients, and that lets us adjust the amounts of each molecule. This makes sure that the number of atoms going in is the exact same as the number of atoms coming out. We're not changing the ingredients themselves, just the proportions in our recipe.
And check this out. This table just lays it all out for us. Before we balanced it, the atom counts didn't add up at all. It was lopsided. But after we added those coefficients, boom, we have exactly 4 hydrogen atoms and 2 oxygen atoms on both sides. The books are balanced, the law is happy, and now we have a correct chemical recipe.
So now that we know the language of chemistry, we can start exploring the different kinds of stories these equations tell. It turns out most reactions fall into one of 4 main categories. Kind of like genres in a movie library. You've got your comedies, your dramas, your action flicks.
This gives us a great little overview. We're going to dive into a few of the most common reaction types you'll see everywhere: combination, decomposition, and displacement. And then we'll look at a really important pair of reactions that are always happening together: oxidation and reduction. Let's meet our main characters.
First up, we've got the combination reaction. You can think of this one as the getting together story. The basic idea is super simple. 2 or more simple things, let's call them A and B, combine to form one more complex thing, AB. A really classic example is burning a magnesium ribbon. The magnesium from the ribbon literally combines with oxygen from the air to form one single new substance, magnesium oxide.
Next up is the complete opposite of that: decomposition. I mean, if a combination is like a wedding, decomposition is the breakup. Here, one complex compound, our AB, breaks down into its simpler parts, A and B. It's the story of something falling apart.
And check out this gorgeous real-world example. When you gently heat these green ferrous sulfate crystals, they start to decompose. First, they turn into a white powder.
If you keep heating them, they decompose again into this reddish-brown solid, which is basically rust, and they release a couple of gases. We started with just one substance and ended up with 3 different things. That's decomposition in action.
Okay, our third type is the displacement reaction. And this one has a little bit of drama. This is when a more reactive, kind of stronger element comes along and kicks a less reactive, weaker element right out of its compound and takes its place. You could call it the chemical home wrecker. So, how do we know who wins the fight? Well, chemists have a cheat sheet for that. It's called the reactivity series. It ranks all the elements from the most reactive at the top, like potassium, all the way down to the least reactive at the bottom, like gold. The rule is simple. An element can displace any other element that's below it on this list. So, for instance, zinc could totally kick copper out of its compound, but it could never work the other way around.
And finally, we've got this 2-part story that always happens together: oxidation and reduction. Now, the easiest way to think about it is with oxygen. Oxidation is when a substance gains oxygen. And reduction is the exact opposite. It's when a substance loses oxygen. It's this constant chemical give and take.
But here is the absolute key point. They never happen alone. They're a team. Whenever one substance is oxidized, meaning it's gaining oxygen, another substance has to be reduced, or losing it. This partnership has a name. It's called a redox reaction. It's basically a chemical trade that happens at the exact same time. So, we've learned the language, we've met the main characters, we've seen the common story types. But so what? Why does any of this matter? Well, it matters because these stories are happening all around you, every single day. Let's bring it all back to the real world.
Remember our question from the very beginning about the rusty nail? Well, here's your answer. Rusting is just a slow redox reaction. It's the oxidation of iron. Iron atoms react with oxygen from the air, gaining those oxygen atoms, and they form a completely new compound, iron oxide. That's a chemical change, a story of oxidation that we see playing out all the time.
Have you ever opened a bag of chips and they just tasted stale? Or smelled butter that's gone bad? Yep, that's another oxidation story happening right in your kitchen. It's called rancidity. It's what happens when the fats and oils in our food react with oxygen, creating new molecules that are responsible for that really unpleasant taste and smell.
Now here's the amazing part. Because we understand the chemistry, we can actually rewrite the ending to this story. We add things called antioxidants to food to stop oxidation from happening. We flush chip bags with nitrogen gas to get all the oxygen out. And just putting food in the fridge slows the whole reaction way down. By understanding the chemical story, we get to control it.
So the next time you see leaves changing color in the fall, or a battery powering your phone, or a campfire burning bright, you'll know. It's not just something that's happening, it's a story being told in the language of chemistry. So I'll leave you with this question. What chemical story is unfolding right in front of you right now?